Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 291, I chat with Starke Sound CTO Dan Wiggins about speakers, drivers, and amplifiers. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com. Hi, everybody. It's time for our annual audience survey. We'd really like to hear from you. It helps us understand our audience better, know what you like and don't like, how you listen to the show. It also helps us tell advertisers what kind of people listen. But I promise you, your feedback is always kept personally anonymous. All you have to do is visit twit.tv/survey and let us know what you think. It'll just take a few minutes, and it'll help us make Twit even better. We really appreciate your support and any help you can give us. twit.tv/survey.
This is Home Theater Geeks with Scott Wilkinson, recorded February 11th, 2016. Episode 291. Speakers and drivers and amps, oh my! This episode of Home Theater Geeks is brought to you by Epson's new EcoTank printers. With Epson's line of SuperTank all-in-one printers, you can print thousands of documents without running out of ink. EcoTank is loaded and ready to print when you are. Visit epson.com/ecotank to find out more. And by Corning Optical Cables. Corning's incredibly durable Thunderbolt and USB 3-point optical cables are longer, thinner, lighter, and stronger. Go to opticalcablesbycorning.com to learn more. Hey there, Scott Wilkinson here, the Home Theater Geek and editor of avsforum.com. This week's guest geek is Dan Wiggins, CTO for a new speaker company called Starke Sound, not just speakers, but amplifiers as well. And we're going to be talking about speaker design and amp design, all kinds of cool stuff. Hey, Dan, welcome to the show.
Hey, nice to meet you.
Nice for you to be here. Thank you so much. Those of you who are tuned in to the live stream at live.twit.tv or logged into the chat room there or at irc.twit.tv can post questions for us as we go, and I'll pass along as many as I can. Be sure to use my screen name, Scott Wilkinson, all one word, no dots or dashes, when you type something into the chat room, because that way it shows up on a different color on my screen and my eye will be drawn to it more readily. So, Dan, this is your first time on the show. I'd love to start with a little bit of background, how you got involved in designing speakers and amplifiers and all this cool audio stuff.
Okay. Well, I've always loved audio my whole life, music, that whole kind of thing. Having no musical talent of my own, I decided I wanted to get into the reproduction side or electronic side, whatever. So got an electrical engineering degree in college. And immediately started working in the acoustics field, but not in audio. It was actually in sonar and ultrasound. So I was doing scientific research sonar systems, did some sonar systems for the military, for torpedoes, moved into ultrasound for Siemens and Medison, doing some high-frequency stuff. But I was always dabbling in loudspeaker design and audio on the side as kind of a hobbyist. Met up with a few other guys in Seattle. We started building some speakers together. They had really good feedback on what we were putting together. So we decided to start a little company at that time. It was Adair Audio. And we started designing just on paper, saying, I think this could work, having other people build them and start making transducers instead of just doing like most of the other small micro companies, which is buying transducers from other companies that were already out in an existing catalog, you know, cracking open the Matasound catalog or the Meniscus catalog or the Parts Express catalog and saying, I'll take one of these and one of those. We wanted to start doing something custom on our own. And just started playing around with that and ultimately transitioned that into a full-time thing where I decided I can make my own. And it took several years and a lot of glue all over the hands and a lot of scraps everywhere. But ultimately, we were making our own subwoofers, and that's kind of what I got known for early on, was making extremely high-stroke subwoofers, affordable subs, especially for home theater. This is back in the early 2000s, kind of at the the big explosion of do-it-yourself subs and home theater equipment, things like that. Did that for several years, got into the production side of things, built some factories, helped Philips build one in Belgium, built one in Chile for another group, and over in China, and just kind of moved on from there. So it really was kind of born out of a love of audio, and just kind of constantly pursuing what could I do that's unique in there, and got into something I found intellectually challenging, which was transducer development. Right.
Well, you know that I don't know if you're a member of AVS Forum, but there's a huge DIY subwoofer group there that they talk about all this kind of stuff, and they build their own sub. I'm not sure too many of them actually build their own drivers, though.
No.
And motors and stuff. You know, that's a whole other ball game, which is what we're going to get into today, which is very, very interesting.
Yes.
Before we do, though, in terms of what you're doing today, let's make sure everybody knows that you, in fact, designed the transducers for the Sonos speaker systems.
Yeah, along the way, I've been fortunate. I've worked for a lot of good companies. Essentially, if you've listened to a Sonos product, you've heard my transducers. If you've listened to recorded music, there's probably a good chance you've heard product that I've either built or influenced. I've done monitor transducers for Mackie and Event and a bunch of other companies as well. Doing microphones right now for Blue microphones for recording studios. So I've gotten into the transducer side of things pretty heavy and all over the very area. Pro sound, consumer, even some laptop work with HP and Apple and Dell.
Well, I've always found it interesting that transducers, that is things that convert one form of energy into another, basically work the same. Although in reverse, whether you're talking about speakers or microphones, they're basically the same thing. Microphones convert acoustic energy into electrical energy. Speaker transducers do the exact opposite.
Exactly.
So, you know, they're sort of, in essence, kind of the same, right?
Very much so. I mean, it's the same physical principles. As one of my advisors in college told us, if you're using more than freshman level of physics, you're thinking too hard. It's really basic. It's, you know, something moves through either an electric field or magnetic field, and you sense a voltage change, or you put a voltage on it inside while something's inside of a magnetic or electric field, and it moves. Very, very similar technologies, both for microphones and for speakers. Obviously, the techniques and the materials and the approach designing it is radically different, but the fundamental principles are the same. So don't overthink it, and you can do it.
Yeah, absolutely. Well, lately you've been nowadays you're working with Blue on microphones, but you're working with this company called Starke.
Yes,
STARKE, Starke Sound. On speakers, and I guess it's a relatively new company, right?
Well, no, actually, that's one of the interesting things. Starke was founded back in 2011, and my involvement with them began in 2012.
Okay, well, you know, under some definitions, that would be relatively new. I mean, when you look at like a Klipsch or something like that's been around 75, 70 years or 100 years or whatever.
Absolutely.
You guys are newcomers on the block for sure, but tell us a little how you got involved there.
It was through a mutual friend. I met Scott Deloche, the principal at Starke Sound, and he had a real passion for building speakers that not only looked great but would integrate well and were designed around home acoustics, real world homes, real world environments. And not finding a lot of that on the market. There was a lot of things designed for very specific placement, but not real world placement. We decided to go at it and look at designing options like that. Along the way, the vision kind of grew to the point of, well, we're not just designing some transducers and cabinets. Let's actually manufacture them ourselves. Let's build a factory from the ground up where we literally bring in raw materials on one side, and out the other end, you get finished product. So you'll end up with us making the transducers, making the cabinets, doing the painting, doing the electronics assembly, everything in-house. And what does that bring? Again, Scott's very passionate about quality and consistency. So we built everything from the ground up with the concept of we're going to own every step of the process so that we can offer a consistent quality experience for the consumer.
Well, it's certainly laudable goal, somewhat difficult to do these days. So many companies, outsource a lot of their manufacturing and so on, and they have to go to the factory where they've outsourced it to and make sure that they're maintaining some sort of quality. You're taking it a step further, really, and making sure that everything is the quality you want it to be by doing everything yourself.
Absolutely. If you're involved at every single step and you own the whole process, not just the initial concept, but you own the design of it, you own the manufacturing of it, and to a certain extent even own the distribution of that to dealers around the world, then it really is your own product, and you can be proud of what you're presenting, and you never have to really sweat about, oh, is this going to be right or is this going to be wrong? Are people going to like it or not like it because it's got some failure in it? We know the intimate details of everything that's in the speaker, and we could stand behind it really well. It harkens back to the early days of Klipsch and the early days of Harman Kardon, when everything was built in-house instead of like now so many companies outsource so much of it. Well, you lose a certain amount of craftsmanship and a certain amount of quality, a certain amount of value in the product, and we're trying to get back to that.
Mm-hmm. So is everything manufactured in the U.S.?
Actually, no. A little bit is. We have two manufacturing facilities, actually. We have one in China and one in Germany. And those are positioned where they are mainly for distribution functionality, distribution flexibility, and consistency. But it doesn't matter so much for us in terms of a manufacturing standpoint of where it's located, because we own the whole process. We own the supply chain. We own the entire manufacturing facilities. We own the SOP, the basic statement of process that tells workers this is what you do and this is how you put it together. We own the quality control systems, so we're able to basically hold a high level standard of quality anywhere we are. So we're positioning our manufacturing at this point where we've been selling a lot. And we really started most of our sales in Asia and Europe. That's where our manufacturing facilities are. We're just now breaking into the U.S. market. So
Got it. Well, the first time I ever heard of the company even, and certainly heard your product, was at CES last month. And I was very impressed. So you and I met there, and I was really impressed with the sound. And so I said, hey, you want to be on the show? And here we are. So let's talk about speakers first, because not only does your company make speakers, but amplifiers as well. And I want to make sure that we spend some time on that. But let's start with the speakers. And give me a sort of an overview of kind of your design philosophy, how you approach the design of your speakers, and what differentiates them from, say, traditional design philosophies.
Sure. It comes from basically, I would say, three things. Number one, it's got to be true to the signal. And what I mean by that is relatively low distortion, great dynamics, relatively flat frequency response. So when you're listening to something, you can actually enjoy what you're hearing, as well as tell the difference between viola and a violin. Is that a cello being bowed, or is that an upright bass being bowed? We want that kind of accuracy in it. So number one, low distortion, good acoustic performance. Number two, it has to be a livable product, which means it has to function in real world environments where consumers actually put things. We all go into the wonderful demo room at a home theater shop or a stereo store, and you've got this big, huge room with tons of acoustic treatment on the walls, and 3 or 4 chairs set up right in the middle in the ideal position, and speakers 3 foot from the back wall and 2.5 feet in from the side walls and set out there, and everything sounds great, but nobody can really afford those kind of setups, right?
Right. Well, some people can, but it's unrealistic to expect everybody to, for sure.
Exactly. That's the kind of thing where you have to literally dedicate a whole wing of your room, of your house, to it. And what we're seeing even in the high end of the market, where people would be able to afford that, there's actually turning away from dedicating space for entertainment. They want to put it more into the whole open concept where I can enjoy my entertainment in the same place where I have dinner, in the same place where we cook dinner, the same place where I read my morning newspaper. I want that large open concept to have that kind of capability in it. So the speaker has to sound good when you place it in non-acoustically ideal locations. close to walls, closer to corners, maybe with some furniture nearby, those kind of things. So that's number 2. And number 3, it has to offer great value. So value is not just about low price. That's about something that part of it is price, but part of it is also quality. How reliable is it going to be? Is this something that's going to blow up? Does it last for a long time? The finishes that are applied to it, the looks of it, does it present a value to the consumer? Does it look high end? Does it have that, wow, this is a really worth what I spent on it? And is it going to be a robust finish that's going to last a long time? Is it a shape and color combination that's timeless and is going to last for the next 30 years? Or is it going to be like that avocado green that was on your refrigerator, 60s, or your shag carpet, right? I mean, some things just go away, but the classic stainless steel, the classic white, that'll last forever. So those are the kind of things we're trying to look for. So those are the way we approach speaker design.
I assume, though, that you're going to approach it as form follows function. You're not going to make a speaker cabinet that fights with the ability of the speaker to produce the best sound it can.
Absolutely. Form has to follow function. You want a great form. You want to make the form look as good as you possibly can. And Scott's a wizard at that. That's really his background, is architecture, industrial design. He's great at that. But at the same time, there's a trade-off of it has to have function as well. So how you blend those two becomes a real difficult challenge. That's one of the big challenges, like at Sonos, how they build product that looks phenomenal and performs very, very well for what it is. So trying to blend those two together, obviously you can't make something that's going to shake your house apart in a tiny little, football-sized kind of product. So we do have to take that into consideration. You can, though, visually minimize the impact of a large speaker in a room simply by making it look appropriate for the room. Make it look like it belongs where it's supposed to be, give it appropriate colors and finishes. So those are some of the ways we kind of hide some of the large sizes. So to a large extent, form follows function, but form also kind of dictates what we can do with the function in that kind of form.
UJ in the chat room is asking a question that was going to be my next question, and he anticipated it. How can you possibly design a speaker that will sound good no matter where it's placed in a room?
UJ, well, that is a big challenge. And to be honest, I don't think you can do it 100%, but there are certain steps you can take that will greatly mitigate the issue. One of the things to understand is that most rooms are relatively small environments, and they have a lot of hard reflective surfaces, a lot of windows, a lot of times hardwood floors. Those are in right now. No more shag from the 70s. So a lot of that kind of stuff's happening. So what you want is a room that is going to maintain a consistent sound on axis, as well as all the reflections you're going to hear. What you perceive from a speaker is a combination of the on-axis direct sound coming right from the speaker, and then everything else that's reflecting all off the sides and coming in and hitting your ears.
Right. We were talking about that last week with Tony and Matt.
Manny. Manny's all about the directivity. Right. Yep. And, part of what he does with his lens is he makes sure that the horizontal response is essentially the same where it goes. So that's a lot of the same philosophies I have, is that, there's two schools of thought. Either try to eliminate all reflections so you only hear the direct sound, but that kind of limits where you could set the speaker and where you can sit in the room. So, or you make it so that the sound coming from the speaker, the off-axis response, both horizontally and vertically, is the same. So the reflections, when they come and hit you, have roughly the same frequency response. Your ear interprets that as part of the original experience. It's perceived more as a spaciousness that may be overemphasized because it wasn't in the original recording, but the echoes tend to have the same kind of spectral characteristics of the direct on-axis response, and it results, in my opinion, to a better experience than having big disjointed responses in terms of the direct reflected sound.
Mahler Music is asking, is the focus more on home theater or music?
Good question. The answer is yes. Well, I mean, now, to be honest.
Good answer.
10 years ago, there was this whole thing of you had to have a home theater system, and that was optimized for big dynamics and low distortion. And that's really what I want about it. I want to be able to shake the floor. I want to feel that gunshot in my chest, pound off, things like that. And then you also had an audio system where you could listen over there and you can enjoy your music. And, it's great on large pieces and on small pieces and things like that. And I think really in the last 7 to 10 years, especially with the advent of streaming music systems and streaming content from the internet, Spotify and Google Music and iTunes, things like that, the two have really started to blend. People want more music in their life overall. Witness the rise of personal music, headphones. Yep. They're much bigger than they are today than they were 10 years ago. Witness the rise of companies even like Sonos, whose whole mission is dedicated to bringing sound wherever you are in your house, music. So the two are blending together. The key now is to make a system that adequately, or I should say more than adequately, in our case, we're trying to just do the high end, but at a minimum, it should convey very good music experience and also have the dynamic capability for a home theater system. And we believe that if you can make an extremely good audiophile grade speaker that has the dynamics required for home theater, then you kind of hit a home run. It's not going to be constrained when you're watching a movie, but at the same time, it's going to sound great when you're using it to listen to music. And that kind of fits in with the whole open concept thing I talked about earlier, where people are moving to much more open concept, less dedicated rooms. They want one really, really good system that will provide the background music throughout their life, but they can still plop down in front of it, throw on Netflix, watch the latest thriller, and just have a blast listening to it.
Mm-hmm. Let's talk a little bit dig a little deeper here. We had one question in here, which is getting kind of geeky, and we're gonna dig into sort of driver design, because I think that's pretty darn cool what you've been talking about. The question is, I'll just pose it real quick here. Do you prefer neodymium to regular magnets in your subs, and by extension other driver assemblies?
That's a tough one to answer. It's entirely application dependent. Really what ultimately matters is the amount of magnetic flux in the system, and do you have enough? You can have too much, you can have too little. Do you have enough? Magnetic flux, as I'm sure everybody's seen the little diagram of a bar magnet with a north and a south and these little lines that go around. And, if you put iron filings down, they go into little lines. That's actually the magnetic flux itself. That's the magnetic field. Flux is a measurement of the strength of the magnetic field. So what matters is, do I have the proper amount of magnetic flux where the voice coil is to get the performance I want out of the speaker? There's multiple ways to get magnetic flux. You can get it with a ceramic magnet, the big, huge ferrite ones. You get it with neodymium. You can get it with samarium cobalt. You can get it with Alnico. You can get it with an old field coil where they literally wind a second coil on there that generates an electromagnetic field. Sometimes it's DC and you get high saturation. Sometimes it's AC. There's, that was kind of the earliest speakers in the 20s were field coils. So you'd plug your speaker into a 120 outlet, and that would energize your magnetic field, and then you would actually have another one going on to it, literally. So, wow, is Neo better than ferrite? Yes and no. If I need small size, like in a car, or I'm trying to make something very, very small and lightweight, or very, very thin, because the amount of flux you can get out of a piece of Neo compared to a piece of ceramic is incredible. It's it's 20 to 1, 30 to 1. Then I would go Neo. The downside is it's a lot more expensive, and it tends to not hold up as well to high heat situations as ceramic. So that may also be a drawback. Obviously, though, if I can tolerate the weight, or in the case of like a large subwoofer at a home where size isn't really too much of a constraint, I probably want something extra heavy anyway, just to help keep the subwoofer from walking around the room, right?
Yeah, you don't want that.
So, trying to save 20 pounds of a subwoofer driver in that kind of a case is kind of a drawback. I might want to actually go ahead and go with the ceramic instead of the Neo, keep the speaker from moving around, have better heat dissipation, and put the money elsewhere where it might matter more.
There you go. Great answer. Yeah. Well, listen, we're gonna dig deep into driver design here in a minute, but before we do, I'd like to take a moment to thank our first sponsor for this episode, which is Epson. Now, Epson's revolutionary EcoTank line of printers for home and office introduce a new age in printing. The new EcoTank ET4550 wireless all-in-one printer doesn't use ink cartridges. Instead, it features an innovative refillable ink tank. It comes with enough ink to print up to 8,500 pages, which is equivalent to about 50 ink cartridge sets. You're loaded and ready to print for up to 2 years. Powered by Epson's leading-edge precision core technology, it delivers high-speed, vivid colors, and laser-quality black text. plus auto two-sided printing, a 30-page auto document feeder, and easy wireless printing from tablets and smartphones. All EcoTank printers deliver an unbeatable combination of convenience and value with ultra-low-cost replacement ink bottles. Now you have the freedom to print without running out of ink. Visit Epson.com/EcoTank today to transform your home, office, or work group the way they print. For the best combination of ease and value, turn to the new Epson EcoTank printers. That's epson.com/EcoTank. And we thank Epson very much for their support of Home Theater Geeks. Epson, exceed your vision. So, Dan Wiggins of Starke Sound, we are about to dive deep into the realm of speaker motor design. We have a number of graphics which you kindly sent, and I'd love to show them as we're talking about them. We're talking first about the voice coil, which is really the thing that responds to the magnetic field, right? You've got the audio signal, as in the form of an electrical signal, passing through this coil of wire in the voice coil, and it that responds to the magnetic field that's around it and causes the diaphragm to move in and out. Tell us about the more traditional designs called overhung and underhung.
Sure. So the voice coil, as you said, is, it's a little round coil of wire, literally, and it's attached to the cone, and it's what the amplifier is hooked up to, and the current that the amplifier puts through that voice coil causes it to react with the magnetic field inside the rest of the motor, the neodymium or the ceramic we were talking about earlier,
right?
And that causes the cone to either move forward or backwards, and how far it's going to move. So overhung literally is just like it sounds. As you see on the motor Cutaway here, there's that red part, and that's the voice coil. The purple is the former. That's a tube that the voice coil is wound on to actually allow it to couple to the cone. The blues all form the metal. The green in this case is the magnet. And so we have essentially, if I'm looking at the magnet and I go straight up, that is the magnetic flux is coming out of the top of the magnet, and then it's going over to the left through the darker blue, through the voice coil to the light blue, and then back down the light blue, up the really dark blue, and up to the bottom of the green, and that creates my magnetic circuit. So overhung literally means the voice coil is hung over the magnetic gap. The magnetic gap is the area defined between the medium blue and the light blue, going straight across to the left. So it's longer than the field of the magnet. That's a very, very old technology, very, very standard. It's incredibly common. It's incredibly useful. It's a very good approach for a lot of things. It's a great way to get a lot of strength to kind of maximize the use of the flux in the motor.
By the way, in that diagram there, which way is the voice coil moving? Where's the direction of the sound coming out?
The voice coil is moving up and down vertically. So it's moving up and down. There's actually something called the right-hand rule. I don't know if you've ever heard of that.
I have, but
okay, cool. If you take your right hand, if you take your right hand and let me get this up here. There we go. See, ta-da. So I do this with it. This is the direction of the magnetic flux. So I got my right hand, my middle finger is pointing over. This is the direction of the current in the voice coil. So it's going around this way. This is the direction of motion. So when my current, my voice coil is flowing this way, and my magnetic swing goes this way. Now, what happens if the current goes the other direction? Or if I'm on the other side, it'll turn around, go back the other way. It'll go back down. So literally, it's just going to move up and down as the current's moving around in the coil. That's just the result of the magnetic force.
And because an audio signal is an alternating current. That is, it goes one way for the positive going part of the waveform and the other way for the negative part of the waveform, right?
Exactly. So it's going to alternate. It's going to go up and down, up and down. The further it moves, the more SPL it generates, sound pressure level. SPL is literally just a measure of pressure. So the more I move, the more air I displace, the more pressure I create. Thus, the louder it gets. The faster I move, the higher the frequency. It's
pretty simple.
Physics.
Freshman physics. We're going to stick with freshman physics here.
Freshman physics,
I myself do have a degree in physics, so that's why I know about the right-hand rule. But nonetheless, we want to make sure everybody knows about that. Okay, then that's overhung. Then what about underhung?
Underhung is kind of the exact opposite. It's where the magnetic gap is very tall, like as this graph shows. The blue is much taller than the voice coil. The voice coil is shorter. So the voice coil at that point is always, as it moves back and forth, it's always in the magnetic field until it moves a fair amount. So it's always a very consistent magnetic field. You get a very even amount of motion for current through the voice coil, but you can't move too much before you start to leave the magnetic field. And as you can imagine, it takes a lot of steel to make a pretty tall part. Underhung is great when you're talking mid-ranges, tweeters, anything where you don't really need a lot of motion in the speaker. You want very, very high accuracy from a very, very linear force. In other words, the voice coil at rest pushes just as hard as if it is a couple millimeters up. It doesn't change much, doesn't modulate its ability to push or pull on the cone very much. So that's underhung. It's, again, a very, very old technology, early 1920s. It's covered in some of the original Kellogg and Rice patents.
Okay. Then next we have something called dual gap.
Yes, dual gap's kind of that's one of the things I invented. It's a combination of both. And it's very much like a stepper motor too, essentially where you have an overhung voice coil. In this case, as you can see the red there, and it's overhung relative to each of the magnetic gaps. You'll see the blue, the medium blue comes together and it's got like a cutout in it, and that forms two smaller magnetic gaps. And so literally it's overhung on each individual gap, but underhung relative to the entire top plate, the entire piece of steel on the top. And so it acts as like a stepper motor, for instance, where you commutate between magnetic gaps. It gives you the best of both worlds. You get a very, very high motor force like you do on an overhung, and the ability to move a lot like an overhung, but you get a very, very linear motion like you do with an underhung. So it's kind of a combination of the both. That was one of the things I patented, and we rolled it out in lots of products. And actually, I think a ton of guys at ABS Forum bought a lot of our tumults that had that and built some really monster subwoofers with them.
Cool.
Yeah.
And then finally, we get to your latest version of dual gap motor design, which is LMF.
Yeah, LMF is we call it linear motor force. It's a very, very interesting approach on dual gap. Dual gap is great. It's very, very useful, very, very popular technology. What we've done here is kind of optimize dual gap for a given operating experience. And we can do this because we know what the subwoofer is going to be doing. We know how much power it's going to get. We know what cabinet it's going into. This isn't just a generic transducer. We know the same thing about the mid-ranges and even the tweeters, because we do dual gaps on those too. And so we do an LMF version. What LMF does is try to balance for the dynamic offsets in the magnetic flux. Basically, as a voice coil runs, it's the simplest way to explain how a speaker works, I always tell people, is you played with two magnets and you put them in one orientation, they want to snap together. You put them in the other orientation, they want to push apart, right?
Mm-hmm. Yep.
So attraction and repulsion. That's literally what a voice coil and a motor are doing. They're two magnets. One happens to be an electromagnet, and that's called your voice coil. And so it's trying to push and pull against it. The more current I put in the voice coil, it's generating its own magnetic field, and that magnetic field is interacting with the rest of the motor. What it's going to do as it interacts is actually depress or accentuate the strength of the rest of the motor. And so I can have a modulation in the whole strength based upon how much power I'm putting in the voice coil. LMF counters a lot of that just by shaping the steel, shaping the pole piece, the top plate, and changing how the voice coil is wound so that we can linearize the motor force, not just with position, but actually with power, and reduce a lot of power compression and a lot of distortion that comes from higher levels of power.
And this obviously is a great goal. And some of the graphics you sent me are so interesting because they reveal what's going on in terms of the force on the voice coil and the resulting distortion. These are the series of graphs I'd like to show next that are called BL. And yes. I asked you, what does BL mean? And you told me.
Well, it's literally engineers we're great at creating acronyms. In this case, it's the B field, which is the magnetic field. That's just the symbol B is used for magnetic field, times the length of the wire L. So that's what it's B times L, or BL. We're not really creative groups. Marketing doesn't like engineers. So,
Yeah, I gotcha. Still, we can take a look at this BL and see how what happens there, and it gives us some good information. Tell us about this first one.
For instance, this is a traditional overhung voice coil. It's very well centered. As we see, the peak of this curve is right around the 0 point on the x-axis. The y-axis here is measuring motor strength. That's in newtons per ampere. Newton is about 4.5 newtons per pound. It's just a measure of force. So that's how strong it's going to push. The y-axis, the x-axis is how far it's moving up and down.
Pardon me. How strong it's going to push given a given amount of current.
Yeah, exactly. Yeah. So for one
amplitude, the amplitude of the audio signal, in other words.
Exactly. In this case, if I put 1 amp into this theoretical speaker, I'd get about 8.5 newtons of pressure as it's at the 0 point, as it hasn't moved yet. Now, let's say it's moved forward 5 millimeters. So you go to the +5 on the x-axis. Well, now if I put that same 1 amp in, I'm only going to get about 7 newtons of force. So I went from 8.5 to 7. And it continues to drop. If I go 10 millimeters forward, I'm only going to get 3 newtons of force.
Now, is that because the voice coil is moving outside of the center of the magnetic field?
Exactly. It's starting to leave the magnetic field, and it's getting weaker as it does. The same thing happens when it goes back. So it's losing the ability to push equally hard. That's one of the downsides of an overhung. It's hard to optimize for that.
Got it. And I assume underhung is similar?
Underhung is similar, although it tends to be very flat in the middle. So instead of having that large peak that happens, it tends to come up, go relatively flat, and then back down. So you have a range of, in that case, maybe 4 or 5 millimeters where it's ruler flat, and then it drops off pretty quick thereafter. So you don't get a lot of stroke out of an underhung unless you have really, really big, thick pieces of steel. But then you're taking your fixed amount of flux out of your magnet, spreading it over a large area of steel. Well, you don't get a lot of force as a result.
And then you can calculate distortion when thinking about things in this way, right?
Absolutely. Essentially, what happens is when the speaker's not able to increment itself properly. So let's say in this case, as it starts to move forward, it's not, for every unit of current or unit of voltage I'm applying on the voice coil, it doesn't move forward the same amount. And it may move forward or backward different as well based upon which direction I'm going. And that's going to cause an increase in distortion. Here we see the THD curve that would result from just the nonlinearity of BL, that BL curve we saw, that sine wave that looked nice and symmetric. This is the distortion curve that would arise from that thing moving forward. So we see on the y-axis, it's percent THD. On the x-axis, it's excursion. So I can see that at 4 millimeters forward, it's around 3-4% distortion. At 8 millimeters forward, it's 18% distortion. At 12 millimeters forward, it's 55% distortion, and it just continually increases at a pretty astronomical rate. So distortion happens just from nonlinearity. In other words, the motor force changing as it moves. That also manifests itself, interestingly enough, as a compression artifact. Everybody worries about power compression, right? I don't want my speakers to power compress. I don't want power compress. Power compression comes from 2 things, really. One comes from thermal. In other words, I just heat things up. And when you heat any metal, its resistance goes up. Expands, resistance goes up. It's harder for a given voltage to put more current through it. That's an easy one to counteract. A voice coil heats up in a matter of tens of milliseconds and cools down on the order of minutes. So when I crank it up, my voice coil heats up, boom, almost instantly, and all I have to do is turn the volume a little higher, and I've counteracted the volume, the resistance change in the original. Not a big deal. You're not going to hear it. It's not a changing thing. The other compression you're going to hear is BL-based compression. Efficiency of a speaker, sensitivity of speaker is proportional to the BL. So imagine I have a speaker that's rated at 90 dB SPL at rest at that 0 value. When we were talking that 8.5, right, in newtons per ampere, is 90 dB. Well, we move forward 5 millimeters, and now it's only 6 newtons per ampere. Well, now instead of being 90 dB, it's 88 or 87 dB. And now it goes even further. Now it's down to 80 dB. So the speaker efficiency is actually modulating as the cone itself moves. That's positional dependent, and it happens instantaneously, and you cannot overcome it with changing the volume setting. It's going to happen on every single musical event. So a lot of times when you're listening to a system and it doesn't really have that really strong dynamic peak impact, it's because the BL is modulating so much that you're literally taking these sine waves that you're putting in and you're just kind of cutting off the top and bringing them back down.
Oh man, clipping, in other words.
It's an acoustical, it's a BL, it's a magnetic version of clipping essentially. And that really squishes down the sound. That's the type of compression. That's why you want to have a very flat BL. It gives you a much bigger dynamic sound.
So the next picture I want to show is dual gap BL. Let me get that right.
Yes.
Which shows sort of more like that plateau you were talking about with that you were talking about earlier.
Exactly. And I want your listeners to understand, for every single one of these comparisons, we use the exact same amount of magnetic material. So the exact same size of ferrite magnet in all of these. So as you can see with the dual gap, we have about the same, or actually a little tiny stronger motor than the original overhung. So I'm 8.5, 9 newtons per ampere. But if you look at it from plus or minus 10 millimeters either way, it's going from 8.2 to 8.8. There's very little change in the magnetic force, the BL, as that moves back and forth. On the overhung, it was 8.5 in the middle, and by the time you move 10, it was down around 4 or 5. So we've lost a lot of magnetic force relative. So that means this one's going to move very, very efficiently. There's not going to be any of that compression or clipping we were talking about, and the distortion as a result is going to be very, very low. It's not going to really start to distort much until you're out 12, 13, 14 millimeters. It's going to be down in the single digits until you get out to that point, and then it'll start rising.
Right. And then clearly, if what you then want to do probably is limit the excursion to where it's in that nice flat area, right?
Yep. As a system designer, I will then say, okay, I know this is the speaker I'm using. This is the size of the cabinet. So the size of the cabinet helps dictate how much cone support I'm getting from the air inside the cabinet. And so, how much is the cone going to move, how much power we're going to apply to it, especially in case of a powered subwoofer. I can then design a transducer that will never leave that area under any kind of operating conditions. So it's just always perfectly linear and perfectly uncompressed in terms of BL compression.
Last two diagrams here in this regard. One shows BL as related to current. You were talking about that before. So let's take a look at that. Tell us what we're looking at here.
Correct. So what we're looking at here are various curves showing how they may offset from each other in terms of applying additional current. This is an overhung speaker. And what I'm doing here is at the green line, that's the nominal BL of the speaker. In other words, when we're
which we saw before.
Exactly. This is typically what you're going to see in a data sheet as if it was tested like 50 millivolts or 100 millivolts. So micro, tens of milliamps maybe in this, a very, very low current. As I turn the current up, for the red, for instance, I'm now at 1 amp input, 2 amp input, which is not a lot of power. 1 amp into an 8 ohm speaker is only 8 watts. It's not a lot. You could see, yeah, I'm getting a little more output. Hey, my motor's getting a little stronger, but we also see there's a divergence. It's starting to shift over to the right. So it's starting to become more asymmetric. Now, as I take it to the blue, which is 16 amps of current, no, not 16, 10 amps of current. So a lot of current into this thing, a couple hundred watts into a 4 ohm speaker. We see we gained even more nominal BL, but it's become very asymmetric, and the distortion is going to go very much up. So this is showing literally how the motor strength not only shifts to one side, but the motor strength itself just changes as the current through the voice coil goes. So this is going to be a very nonlinear sounding speaker.
Got it. And then finally, we have a graph here of the BL for the different designs sort of superimposed on one another. And I found this very interesting as well.
Yeah, so what we're showing here is what happens with all the various designs. The green here is an underhung. It very good, but as you can see, it's incredibly limited in stroke. It's starting to fall off when you get plus minus 5 millimeters. It's like, hey, you're doing a good job, but stay in the minor leagues. You just don't have enough to do what we need to do. The red is very much what happens when you really start pushing an overhung really hard. Yeah, you get a ton of BL, but look at how asymmetric that is. It's centered out about 8 or 9 millimeters forward, and it's rapidly falling off on either side. You basically have created what's called an offset. So your speaker at this point, sometimes, I don't know if guys have actually watched their subwoofers under high power, sometimes it looks like the speaker will just kind of throw itself forward and then oscillate about this forward point. This is showing exactly why that happens. It's basically recentered itself. It'll happen from BL doing this. It'll also happen from a suspension issue too. But a lot of times it's simply BL. And so it's recentered itself, and now everything's nonlinear. The third is our LMF optimization, the blue, which is, hey, you know what? We've tried to keep it as linear as possible. Same amount of current. You can see there's very little change in the BL curve over plus minus 10 millimeters. You know, it's changing 15%, 10%. And it's incredibly flat and very wide. That's going to have the lowest distortion and the most consistency out of all of them.
Got it. Well, we've got a lot more to talk about, but before we do, I'd like to take a moment to thank our other sponsor for this episode, which is Corning Optical Cables. Now, Corning has transformed the traditional USB and Thunderbolt cables from plain old copper into incredibly durable fiber optic speed demons. Whether you're into high-end video, photography, audio production, or computing, you want the best, most reliable cables out there. So I'd love for you to take a look at Corning's Thunderbolt and USB 3-point optical cables. Corning is known for fiber optics, and when you think about fiber, you think of glass, and glass breaks, right? Yet Corning has figured out a way to make their USB and Thunderbolt cables super strong and flexible. So flexible, in fact, you can bend them, walk on them, even tie them in a knot, and they still keep transmitting at top speed. I like to show this example here. I've got a Corning USB 3-point optical cable that's powering my printer, that's sending data to my printer, and I've tied it into a tight knot here, which I at first was a little hesitant to do until a Corning guy said to me, no problem. And he showed me, he just yanked on it, made a super tight knot here, still transmits fine. The printer prints things at normal speed. It's really quite remarkable. And speaking of speed, Corning fiber optic cables provide incredible data rates of up to 20 gigabits per second for Thunderbolt and 5 gigabits per second for USB 3. No other cable comes close. Another interesting fact is that Corning optical cables are 50% thinner and 80% lighter than traditional copper cables. Corning optical cables have exceptional cable runs up to 60 meters or 200 feet for Thunderbolt and 50 meters or 165 feet for USB 3. Now you can declutter, moving peripherals to another room, improve productivity, and increase security by putting expensive gear out of the way. Corning optical cables are longer, thinner, lighter, and stronger. Go to opticalcablesbycorning.com to learn more. And we thank Corning very much for their support of Home Theater Geeks. So in the time we have left, let me see if there are any questions in the chat room here. Let's see. SoundPro 69 says, correct me if I'm wrong, but I don't think I've seen these types of graphics in speaker reviews. And for what I'm hearing, it should be very important. Not a question more than a comment, but I think he's right.
100%. You know, I mean, there's so much of a bias in a lot of the media about, you know, trying to dumb it down for the listener, whereas I think we should try to, you know, educate the listeners, educate the readers, right? Let's not try to dumb things down for people.
I totally agree. Lawn Dog says, if you're shooting for a flat response, do you mean that when music is played, you'd like to set the bass, mid-range, and treble at 0 and have an accurate reproduction, or maybe a sound that's more pleasing to the ear? This gets into the notion that I've known or thought for a long time about the difference between consumer speakers and professional, you know, studio monitors, where the monitors, they want to be super flat, super accurate. They don't want any sort of coloration. Whereas with consumer speakers, I've often heard it said that, yeah, they're kind of tuned to be more quote unquote pleasing to the ear. Do you think that's a valid assessment of the consumer versus professional market?
I think it is. I mean, the consumer market is, well, I'll start with the pro market first. The pro monitor is a tool. It's no more than the mixing board. It's no more than the headphones. It's no more than the microphone preamp or the mic. It's a tool used by the engineer and the artist to create an experience that they want to convey to the listeners, to the consumer. That's all there is to it. It's a tool. So obviously, you want the tools to be as neutral or as predictable as possible. Like if you're a carpenter, you want your saw to be straight and true. You don't want a saw that's like this because you can't cut anything, right?
Yeah, right.
You don't
right.
want a wobbly end on your drill press. It doesn't
Right.
work. So it's a
Right.
tool. It's got to be accurate. It's not really meant for musical enjoyment. Doing a speaker for musical enjoyment.
Yeah, I was going to say, wouldn't a consumer want that also? Want accuracy?
It depends. This is an interesting little debate. I come down upon it. There's always the whole accuracy versus coloration, things like that. I break it down into what I've learned over the years is there's what you hear and there's what you perceive. They're two different things. And there's like the Franson effect, and there's some other little audio tricks that you can do that are really wild that show that what you're actually hearing, the physical event you're hearing, is not what your brain perceives. Okay.
Wow. Okay.
There's things that happen in there, like so people can go out and look up some of these things on the internet. The Franson effect is a really interesting one about precedence and how your brain locks on to certain events, and then even though it's coming out of the left speaker, you're still hearing it as coming out of the right speaker because that's what your brain said had to happen because of what it experienced earlier. So it's like little illusions that can happen audibly. So not necessarily completely flat is not necessarily what people really like. Everybody likes their own things. I mean, I guess you could say the most accurate way to eat a steak is just to take it, cook it over a flame or on your grill and eat it. However, a little bit of salt, a little bit of pepper goes a long way to actually enhancing the flavor of the steak, and it opens up your taste buds to the point where they can fully enjoy the flavor and enhances the flavor. Is that accurate? Well, no, because I've added something to it. However, at the same time, I'm able to better perceive the taste of the steak, and I'm able to better enjoy the steak itself. So why would I not do that? So
great
I always try to break it down. Really cool. Yeah, I mean, there's the production, and then there's the reproduction side. And production's done about trying to create an event. Reproduction's about trying to enjoy the event, and that necessarily leads to different goals.
Lawn Dog is asking, do you and Starke rely more on measurements? He's saying measured frequency response, but I'll include other measurements as well. Or does creating a speaker that sounds pleasing? In other words, the basic question is, what's the relationship or the ratio of measurements versus subjective listening that you apply to your speakers as you're developing them?
I would say it's almost 70-30 measurements to subjective listening. But understand there's a bit of history in here. Early on, I would sit down, I would build something I thought sounded good, and I'd kind of tune it by ear. I'd have other people sit and listen. They'd listen to it and say, that sounds good or bad. And then I would go and measure it and measure every little thing I could so I could kind of capture that and say, oh, next time I'm going to design something, I can objectively measure in my lab, make sure I'm kind of close to that original stuff I had, and then get people to hear it and refine. So after a while, you get to a point where you have a set of measurements that you want to achieve, and you already have a way of linking. If I measure X, I'm going to have preference Y, and those kind of combinations. So we do a lot of measurements right out of the gate at the lab, a lot of the early development. But then as we're getting close to finalizing the speaker, we'll sit down and we'll all live with it for months. We'll put it in front of other trusted ears we have for months. We'll get feedback. We'll tune as needed. But the longer you've been at this, the more you're able to tie the relationship between what I measure in my set of measurements versus what people are going to hear. And when I can make that linkage, it allows me to move faster because I can short circuit a lot of the got to listen for years and years and years. Now I have to listen for weeks and weeks and weeks. That's a big advantage. And it also allows us then to reproduce the same kind of sonics right away. I know that if I build a small three-way cabinet for like a bookshelf and people really like the way it sounds, if I properly capture the distortion, the frequency response, the phase response to that in 3D around it, and then when I build a full tower that has the same kind of distortion, phase response, frequency response in the same bandwidth, they're probably going to sound very much the same. I'm going to get the same kind of feedback from people. And as it turns out, that actually happens.
This reminds me a little tangentially of you remember the movie The Matrix, of course.
Yes.
And at one point, Switch, I think his name is talking to Neo, and Neo's looking at the Matrix in code, and he's saying, "Can you read the code?" He goes, "No, but well, I've just kind of, all I see is blonde, brunette, redhead."
Yeah, exactly. Yeah.
So he's looking at the code, but he's in his head, he knows what it means, and he's seeing it almost immediately.
Exactly. How you tie those together becomes the important part.
Right. Creamy Corn Cob is asking, and you'll have to explain this a little bit. When working with teal small parameters to design a driver, do you prefer a rubber surround or a foam surround? So first of all, explain what are teal small parameters?
Teal small parameters are ways of making physical mechanical systems easy for us stupid electrical engineers. It's a way of breaking it down and measuring things like the resonant frequency, the Q, which is a measure of how the energy is dissipated versus how large the energy is, the stiffness of the actual suspension elements itself, which is really just a 2 or 3 element spring, for instance. It's a way of breaking down the performance, the fundamental basic performance of a speaker into a few easy numbers that you can then put into some pretty simple equations, and from that decide how big the box has to be. Do I want to put this in a ported box or a sealed box? Those kind of things. It can give you an idea about the efficiency of the speaker. So it's pretty basic parameters kind of governing how a speaker works at a very entry level kind of thing. As far as foam versus rubber surround, there's not a lot. I've done very low VAS, so very stiff spring rubber surrounds, very stiff spring foam surrounds, and very soft of both. There really isn't a dictator on the foam or rubber that's going to tell you you're going to have this kind of a TS parameter set or another kind of a TS or teal small parameter set. I personally, though, however, prefer rubber surrounds in my mids and my tweeters. Mainly because they tend to absorb sound that's transmitted into them. So they damp the edge of the device much better, keep it from sounding as bad, cone breakup, things like that. I like it from that standpoint. For woofers, rubber's good. A lot of times foam is a little better. It tends to be a little more linear. It's a man-made material. A lot of butyl rubber is man-made as well, but it still has a fair amount of content in it that's a natural rubber. It tends to be a little less linear, a little less predictable. Foams had a reputation for disintegrating, falling apart 20, 30 years ago. That was solved 15 years ago with a lot of fungicides and UV protectants added into it, but they still have that carry-on legacy. So if you're offering a $10,000 speaker, it's hard to justify foam surround on it, for instance. Everybody's going to look at it and say it's cheap. So you may have to use rubber as a result.
Oh, wow. So more for a marketing or a perceptive thing than for an actual physically reasonable approach.
Exactly. I mean, if you take a brand new 2015 Vet and you give it great body work, so you paint, it's all got perfect paint, and it's polished, everything, it looks just great. People are going to say, oh man, that's just awesome, and it goes so stinking fast. Take the same Vet, scratch the crap out of it, take a ball peen hammer to it, beat the snot out of it. Everybody's going to go, oh, it's not very fast. It can't be. Look at it, it's all beat up. So unfortunately, a lot of times our perception of what we're going to experience is heavily colored by what we see. So there's some of that goes in there. But my personal preference, if it's for a system I'm building only for myself, I'm probably going to have a foam surround woofer and rubber surrounds on my mids and tweets. But again, that has to change based upon price, based upon performance, what I'm trying to achieve. Is it going to be exposed to the elements all the time? Does it need to be 100% waterproof so I can literally suspend water in it? And does it have to carry a premium finish? In other words, hey, if it's a $199 speaker product, we're going to wrap it in a vinyl, a wood grain vinyl. If it's going to be a $20,000 speaker, it's going to have piano gloss or hand rubbed real veneer on it, kind of a thing. So you got to take that into account too.
And just for those who might not know, the surround is the material that actually attaches the vibrating cone or dome or whatever to the frame of the speaker, and it has to vibrate, so it has to undergo. It undergoes physical stress all the time.
Yeah. I mean, like people, a lot of guys in mechanical engineers that talk about, oh, yeah, I made this spring to handle 100,000 operations. Isn't that amazing? Or this connector takes 20,000 insertions. And I stop and think, the last tweeter I did does 20,000 operations in a second.
Yeah, right.
and it's going to run for 30 years. It's got a 20,000 hour life cycle, and every second it's doing up to 20,000 operations. So these surrounds are moving a huge amount all the time, hundreds and hundreds or thousands of times a second. So it's a testament to design and materials that they can handle that long.
Well, in the few minutes we have left, I'd love to talk about amplifiers because not only do you make speakers, design speakers, and Starke makes speakers, but also amplifiers. And what we saw at CES was truly remarkable. It was a pure Class A amplifier producing 450 watts per channel times 7 channels.
Exactly.
Now, that is really amazing, and I'd love for people to understand why that's amazing. So let's quickly go through the different kinds of amplifiers. We got some diagrams. Thank you very much for finding those on Wikipedia. I should have and could have done that myself, but you did it for me, and I really appreciate it. Let's start with Class A, which seems to be sort of the simplest kind of thing to think about.
Class A basically is a system that always conducts. So it's the output device is the output FET or transistor is always conducting electricity. It's never off. So the device never distorts. It's always on. It's always doing something. You get the best sound from it. I don't think anybody's going to argue that. The issue is it's highly inefficient. A good Class A amp is usually 10 to 15% efficient. It means if I want 1 watt out, I'm putting 10 to 15 watts in. If I want 10 watts out, I got 100, 150 watts just dissipating in my room. So it's not a very efficient topology, but it's absolutely the lowest distortion, highest audio quality out there. The best amplifiers in the world, like the top end Nelson Pass designs, Pass Labs, they're all Class A.
Yep. And then we have Class B, which does something really interesting. It just amplifies half the signal. What?
Yeah, a Class B transistor bias by itself essentially only operates halfway. Now, a lot of times you'll take a second transistor and then try to amplify the lower half, and you look at it and go, well, I can have one doing the upper half, one doing the lower half. Great, everything's fine. The problem is a transistor never actually gets down to 0 volts. They kind of shut off when you're a couple tenths of a volt or maybe even as high as a volt off from ground. And so when you switch from your upper half to your lower half, there's this little range in between where neither's conducting. You get a sine wave coming up and then it goes dig, dig, dig. And then it conducts the second half. That's called crossover distortion because you're crossing over the 0 point. And you get a lot of distortion there. Class B, though, is a very efficient linear transducer, linear amplifier design, 60, 70, 80% efficient. It's great for telecom, for radio, when you need to put out a lot of power and you don't want to, heat the world with it. So,
and you don't care that much about fidelity.
You don't care that much about fidelity, especially if I'm just using it as a radio, an RF amplifier where I'm looking to modulate a signal. Guess what? The crossover distortion's above my range of modulation, so my FM or AM is going to sound fine. Be efficient, use a linear I want a linear amplifier, Class B.
And I think you were mentioning before a Class AB, which combines A and B, I guess, with 2 different transistors, one handling the positive going and one handling the negative going, as you see here.
Correct. And what we would do is it's a Class B, but I add a little bias to each one so that it doesn't actually turn off until it's like a volt or a volt and a half past the crossover point. So at very small signals, both of them conduct all the time. So it's like a Class A at very low signals. At highest signals, it's a Class B, but when the voltage drops down, it goes to Class A and then goes back to Class B. So I eliminate most of the crossover distortion or all the crossover distortion if I do it right. I give up some efficiency. So I'm looking at efficiencies of 40 or 50%. This is by far and away the most common topology you're going to find in linear amplifier design is a Class AB. You're looking at pretty good efficiency. You're looking at pretty darn good sound quality, and it's really not that difficult to make.
And then let's touch briefly upon Class D, which many people call digital amplifiers, which sort of are, but sort of aren't, right?
Correct. Class D, basically, this is a real great example. Essentially, it creates what's called a pulse width modulated. In other words, basically, I'm going high or low, on or off, output relative to what my input signal is. So literally I'm deciding, on these output FETs, do I connect the load to a power rail or do I leave it connected to ground? One or the other, switch it high or low. And I switch it at a very, very, very high frequency so that if I looked at an oscilloscope, it looks like just a bunch of data flipping back and forth. It's zeros or ones. But if I take it and I run it through a low pass filter, just to the area, the frequencies of interest, I'm going to actually get a sine wave output. This is tricky to implement at very high powers. It's getting a lot easier all the time because, IC design and technology is moving forward. But it has tremendous amounts of efficiency. You can reach efficiencies in 94, 95, 96% efficiency. So
Yikes.
Suddenly instead of, so a class, think about it. You got a class A doing maybe 10% and this is doing 95%. Wow, you can do things amazing. So class D is great when you need high efficiency. It can lead to a little bit of a noise issue or a little slightly higher distortion. It's usually not critical for a subwoofer, and a subwoofer is where I need maybe 1,000 watts. Well, I don't want to have a 1,000-watt Class A amplifier out there because it's going to throw away 9,000 watts of heat. This guy would throw away 50 watts of heat. Oh, cool, great, that's great. So I'll go with Class D.
Which is why Class D amps have been used in subwoofers for quite a long time.
Absolutely.
But only recently have we seen, full range Class D amplifiers become available for, high-end audiophiles and people like that, because up till very recently, they haven't really done the job over the full range of frequencies.
Yeah, it's hard to switch your amplifier, your carrier frequency at a high enough rate so that your low-pass filter doesn't affect the audio quality and the bandwidth you want. I mean, you have to switch it hundreds of kilohertz or a couple megahertz to make it sound good. That's hard to do at high power, simply put. So
Right. So then the last two graphics I'd love to show here are Class H and Class G.
Correct.
And these are a little bit different than the graphics we've looked at up till now with the amplifiers because they're showing basically sort of the limits to which the signal can vary up to the positive voltage and down to the negative voltage. Let's take a look at Class H, I think is the next one.
Yeah, this is Class H. So essentially what Class H is doing is basically, it's not really an output topology like the other ones we've seen. This is a power supply topology. So what it's saying is let's have multiple power supplies in here, or in this case of the Class H, let's have a power supply that can change its rail voltage. So according to the input signal, so that I constantly am moving my amplifier, my rail voltage up or down based upon my input signal. The dissipation, the loss inside of a speaker comes from all the power it has to dissipate, all the voltage it has to burn away from the power rail, the voltage rail, down to the actual signal level. So if I have very low signal level and I have a very high power rail, I have a lot of heat dissipation in my amplifier. Well, what if I could turn that voltage rail way down so it's just always just barely above the output signal I need? Well, guess what? My efficiency really goes through the roof, and I can optimize my efficiency. That's Class H. So it tracks. It's called a tracking power supply. A lot of times you'll see that. It's an older technology. It's been around for 20, 30 years, but it works really well. That's the key to our A7 amplifier.
There you go. And unfortunately, I should have shown Class G first because that's the step before variable power rails. So let's take a look at Class G real quick. This just switches between two different static power voltages, right?
Correct. Yeah. So anytime I'm using the plus VS rule level there, I'm dissipating one set of power. But when I switch up to the plus VSS power rail, boy, I'm going to have more potential swing there, but I'm not dissipating any extra power because I still have the same kind of difference between my signal and the power rail itself. So it's a good way of saying Class H just basically eliminates those areas you can see between the curve and the red and blue squares that are bumped out. So we use Class H and to great effect, and that's how we're able to do an amplifier that has 7 channels, 450 watts, pure Class A, and a lot of people walked into the room and said, "What? That's not possible."
That's what I said. I was one of them.
Yeah, you're like, where's your 300-volt line, your 380-volt line?
Yeah, really. And where's the air conditioner?
Exactly. Well, go ahead.
Sorry, go ahead.
I was going to say, when you turn the power rail down to the point for most of music and movies and things like that have what's called a crest factor, which is a ratio between the average power level and the peak power level, and it's 20 or 30 dB. Well, that means a factor of 100. So I may need 1 watt consistent to have my movie, but I'm doing these bursts of 100 watts. So why not do a power supply that's mainly putting out just enough voltage for 1 watt, but when it needs to, it'll bounce up to do that 100 watts and then come right back down and do the very little thing, just so we dissipate very little power the whole time.
So what kind of efficiency are you getting with that amp?
Here's the thing. We're getting the same 15% as a Class A amp. But the difference is your average listening level in a home theater type of situations is about 2 watts per channel. So overall, I've got 14 watts out. Let's see, times my efficiency of 15%. I'm doing about 100 watts heat dissipation. It's not a lot of heat I'm dissipating at all on average. But I have the capability to burst to a full 450 watts for each channel as needed. So that's the advantage. I've got the same efficiency penalty I'm paying with Class A. However, I'm minimizing it by not always having all that extra. So it's basically, it's always 10% of whatever the output signal is, not whatever the potential output signal is. That's
right. That's the big difference. A static rail voltage that you're always having it out to that what you think will be the maximum. But if most of the time you're spent in a very small amplitude, you're wasting so much more power than if you're doing it with a variable rail voltage.
Exactly. So that's how we're able to get away with it. And that's why, people would come up and they touch them like, well, these things are just barely warm. It's like, well, yeah, because they don't need to do much, because even at as you experienced, a very loud listening capability, you only need a couple watts a channel on average. You need 300 or 400 bursts. But overall, on average, a couple watts you're idling at, you're fine.
Well, I have to say, as I said at the beginning, that what I heard in that room was really remarkable. It sounded fantastic. And it had to do, I'm sure, with the amps and the speakers, all of which were combined together in a kind of a funky, hotel room, which most hotel rooms are. And it still sounded just great. So I want to congratulate you on a wonderful performance at CES.
Well, thank you. Thank you. And it was a fun time to do it.
Yeah, you bet. And thank you so much for being on the show. We've run out of time and covered a lot of ground, and I want to thank you for that as well.
Thank you, Scott. It's been a fabulous time to talk about it. Anytime.
You bet. I'll definitely have you back because there's plenty more to talk about for sure.
Oh, yeah.
You can find out much more about Starke Sound speakers and amplifiers and products and so on at starkesound.com, and that's STARKE sound.com. You can always find me, of course, at avsforum.com. You can email me at scott@twit.tv, and you can follow me on Twitter at htgeekscott and at avsforum. You can always find previous episodes of Home Theater Geeks right here at twit.tv/htg and on our YouTube channel, youtube.com/twit Home Theater Geeks. Next week, I am planning to have someone here to talk about the Grammys. Don't know quite who it is yet because they are deep in preparation for that. That show is going to be on Monday the 15th. And on the following Thursday, I will be speaking with someone from the Grammys about the show and how it's put on and the whole production and all that jazz. Should be really fascinating. So I do hope you will join us for that. Until then, geek out.